Okay, welcome back, everybody. So, as I mentioned yesterday's announcement, hopefully this will be the last of the disruptions in the normal lecture schedule, and we'll be um, we'll be on a pretty regular schedule. Well, I mean, it's already been a regular schedule, but these first couple weeks having 8 lectures that are 20 minutes longer rather than 10 lectures that are 20 minutes shorter. It's fine. It'll all work out. Okay, so what I stopped with discussing last time was trees. So I gave a very basic definition of a tree. We'll see that there are, in fact, other ways to define trees, but they're all equivalent to this way. So, what was a tree? It's a connected graph that contains no cycles. If you're saying it in a snappier fashion, you'd say a connected acyclic graph, G. So here is an example of a tree. Here's an example of not a tree because there are these cycles that I showed last time. Okay. So it turns out this is very restrictive on what the graph can look like. Restrictive enough that you might already be thinking to yourself, well, starting with small orders, I can kind of enumerate what trees are even possible, right? The textbook, I'm going to give a quick example here. So this one's a tree. This one is a tree. This one is not because it has these cycles. D is not a tree because it's not connected. Right? So D doesn't have cycles, but it's disconnected. Now, we'll see that the graph D really consists of 2 trees, which we'll call a forest. So this is a forest of trees, so it is a forest of 2 trees in this instance, but it is not a tree itself, right? Because both of these connected components taken together are the graph D. So yeah, this is a forest. And then E is also a tree, right? So E is also a tree here. You might notice that in a tree, it seems like we have a lot of these sorts of vertices. What do I mean by these sorts of vertices? So in A, it would be all these on the outside of the tree. Here on E, it'd be everything except this one. B, it would be these, well, and one on the end here. What am I pointing out here? What am I pointing out? I'm pointing out the degree 1 vertices, right? So I have these degree 1 vertices in these trees. Even, like I said, even in D, if you just look at the connected components, you also have these. These degree 1 vertices, there's seems to be a decent number of those. We'll see how many are required here in a little bit. But if I'm thinking like artistically representing tree in this way, what do these degree 1 vertices represent in the tree? Especially with this picture, maybe you could see it. These are the leaves of the tree, right? So we call those degree 1 vertices leaves. I'm going to write all that stuff down here in just a second. But as wrote before, a tree is a graph G that is connected and acyclic. So it contains no cycles. Now, as I said, we're going to see that this definition could have been altered slightly, and it actually wouldn't make a difference because there's a couple other conditions that are equivalent. So, for instance, we'll see that this puts a massive restriction on the number of edges that are possible in the graph. So the edge set is very, very restricted here, as we'll see very shortly. But as I say, a forest is a disconnected graph. Technically, do I want to say that a forest is... Maybe I should say I don't want it to be necessarily disconnected, because then I would have to have at least two components. We could say that a tree is a forest with one component. So a forest is a graph consisting of k trees. So if k is bigger than 1, these trees are the connected components of the disconnected graph. Yeah, this will make at least one statement that I want to make slightly less awkward later, so this is better. Okay. A degree 1 vertex in a tree is called a leaf. So a vertex that is only adjacent to one other vertex is called a leaf. Okay. What are some types of trees from what we know? So some trees. Well, those are those are certainly trees. So connected and acyclic, K1, of course, is just a single vertex. That is a tree vacuously. K2 is also a tree. Okay. Now those, of course, are very, very small. So what are some other trees? What about like piece of tin, the path on n vertices? I'm not gonna draw all of them. You get the idea, but that's a tree. Of course, so is the path on 1,000 vertices, for that matter. What about some of these complete bipartite graphs? Right, is that a tree? What would that look like? This would be, here's one vertex, and then I have 1,000 vertices here. I don't care. I get the idea here. These are not vertices. Right? That's a tree and doesn't contain any cycles, and it's most certainly connected. In the textbook, the authors refer to K1 as a stump and K2 as a twig. I'm not going to do that. I'm just going to say K1 and K2, but it is funny terminology since these are like the shortest trees, right? These are the tiniest trees that we can talk about. In fact, as I said, we can enumerate these for small order, and it's pretty easy to see how this massively restricts the structure these things can have. So I'm just going to give you a picture of trees of order 6 or less and what they look like. There. So you see there's K1, K2. The path on 3 vertices is the only tree of order 3. So there's only exactly one of these for the first three orders. For order 4, you have a path on 4 vertices, and then you have this. For 5, you have path on 5 vertices, and then you have this. You can even see how, like, the path is almost the basic thing, and then you can get these other graphs by doing this sort of thing. See what you're doing here? In each case. So, and you can reason with yourself a little bit, especially in the cases of orders 5 and 6. Reason with yourself that there are no others, right? So try to construct another one and then explain to yourself why this is one of these already. It's isomorphic to one of these already. Okay, so probably, since I know that many of you that are currently in this class have interest in graph theory coming from the CS direction, which is very natural. That's one of the most common places this comes up. Then no doubt you are aware of at least a couple of these applications. But what are the ideas here? So, like, what's the point of trees, right? And where do they arise versus maybe a more generic graph, right? That can be more naughty in a way. So just a few applications. There are modeling. There's like a you could call it like a more generic decision tree or outcomes of an experiment. Here's an example, right? Say I flip a fair coin. If the coin lands on heads, I roll a d4. There's a four-sided dice, all right, four-sided die. And if it lands on tails, I roll a d6. I record the result in either case. What does modeling all of the outcomes look like? So the first vertex I start at is basically before I've flipped the coin. Flipping the coin, there are two options. There's heads or tails, right? So heads and tails. So we could have this vertex represent heads, this represent tails. Then if it lands on heads, I roll a d4. So from heads, I would get 4 options here. Maybe I label those 1, 2, 3, 4 to keep them separate from the vertices over here, right? I could label these. This is the one you get after rolling heads, 2, 3, and 4. Whatever. You wouldn't have to do that. This is just something I'm doing right now. Tails, I roll a d6, so there are 6 options here. All right, 1, 2, 3, 4, 5, 6. Okay, so starting here and then traversing this structure, right? I end at one of these outcomes down here, and of course, maybe, right? If we're interested in answering some probability questions, I could even write some probabilities on edges here, right? And say it's a fair coin, so these are both 0.5, 0.5. Maybe the die that I'm rolling is fair. Maybe it's weighted, right? So maybe this one's fair, but this one's not. right? So there's like a 50% chance to roll a 1, as it can never land on 2. There's all sorts of things I could do here. But what am I doing here? I'm like putting some kind of weights on these edges. Now that has nothing to do with the tree structure, but this just naturally arises as something I might be interested to do in this context. And we're going to talk about that very shortly, this notion of when it might make sense to have weights on these edges and then ask questions about those sorts of things. It's a type of weighting function applied to the edges here. Again, that has nothing to do with the tree structure. I just added that. So the whole point is that this is a tree. Okay, the resulting thing is most certainly a tree. You can just check, of course, it has no cycles and it's connected. Okay. What else? Of course, you see this, right, and you know anything about basic like programming logic, and you'd recognize that, oh, well, this sort of thinking of it as outcomes of experiment, I can also, of course, think of a binary decision tree as a more rigid form of that, or more simple form of this, where at every step there's a binary option. So binary decision tree. Of course, the words match up. It is literally a tree in the graph theory sense. So maybe rather than list example, find, say, the max of 4 numbers. So find the maximum element in the set of numbers x, y, z, w. And rather than write this out, I'm just going to give you the binary decision tree here. So here's the question. First question, is w greater than or equal to x? Yes or no? If yes, is it greater than or equal to y? If yes, is it greater than or equal to z? If it is greater than or equal to all x, y, and z, then it is the max. If I get to z and it is greater than or equal to x, greater than or equal to y, but not greater than or equal to z, which means z is strictly greater than w, this means that z is the max. If w is greater than or equal to x, is not greater than or equal to y. If y is greater than or equal to z, then y is the max. If it's not, then z is the max. And so you see how this process works and how we have modeled it in this way, but stripping each of these questions out. Of course, each of these are just vertices, and all of these would be the end vertices representing, again, the end of this process. Okay. All right. There's the chemistry application. You might have, counting some of these trees of some order, might have made you see, oh, hey, I've seen some of these from my chemistry class before. I've definitely seen some diagrams that look like this. So, saturated hydrocarbons. So things of the form CnH2n plus 2. So propane, ethane, pentane. I'm going to go ahead and put those here on screen. And actually, not only is this a useful representation, but even in the graph theoretic sense, in ethane, propane, and pentane, the vertices of degree 4 are the carbon atoms, and the leaves are the hydrogen atoms. So even the terminology that we've come up with for these trees actually applies in the underlying chemistry. Degree 4 vertices are the carbon atoms, and the leaves are the hydrogen atoms in all these diagrams. Okay. One last application that I'm not even going to write down, of course, is if you're looking at like a March Madness bracket, right? Here's the Men's Sweet 16 from 2008. This is what it looked like. So that is also a tree. Okay. So the thing that I mentioned immediately was that a tree, requiring a graph to be a tree, is actually a huge burden on its existence. It's a giant restriction. To see how giant of a restriction it is, you have the following theorem, which is, well, the theorem says if you know what the order of the tree is, you know exactly how many edges it has. And if a tree T has n, or has order n, we'll say, then T has n minus 1 edges. So that is very restrictive. It's not a bound on the edges. This is saying it has exactly n minus 1 edges. So if you have a graph of order n and it does not have exactly n minus 1 edges, it cannot be a tree, right? Because if it was a tree, according to this theorem, it would have to have n minus 1 edges. And so, how do I prove this? So I'm inducting on the order of the tree here. So I want to do induction on order of t. So base case, n equals 1. The only tree is the complete graph on one vertex, which is just a vertex. And so, of course, there are 0 edges. And 0 is, in fact, 1 minus 1. Right? Here, I'll write it just to do it. It has 1 minus 1 edges. Okay. So, assume the result is true. Is true for all trees of order less than k. And let t have order exactly k. We want to show that t also satisfies this, has k minus 1 edges. So choose an edge of t, any edge. Call it E. Question. What does t minus E necessarily look like? Now, this is going to be one of your homework problems that I'll assign tonight, and your homework that I assigned today will be due on Friday, and then I'll assign homework 3 on Friday, and it'll be due the following Monday or maybe Tuesday. So just letting you know. So this is going to be one of those things, actually proving this, but it turns out that t minus E has to be disconnected with 2 connected components that are trees themselves. So it turns out, you will prove this in homework too, that t minus E is disconnected with 2 components that are trees, i.e. T is a forest of two trees. Okay. Call the components of T minus E, T1 and T2. If the order of T1 is K sub 1 and the order of T2 is K sub 2, then both K1 and K2 are less than K, and they sum to K. Think about why that is for a second. Of course, we removed an edge. We did not remove any vertices. Right? When you do edge deletion, you're not removing vertices, you're just removing the edges indicated. So we only removed the edge, all the vertices stayed. And so these are K1 plus K2 is definitely all of K. It's all K vertices in the original graph or tree T. Okay. Now, by the induction hypothesis, since K1 is less than K and K2 is also less than K, the result is true for both T1 and T2 separately, i.e. T1 has K1 minus 1 edges, and T2 has K2 minus 1 edges. But the edge set of the original graph T is just the disjoint union of the three sets of edges, the edge set of T1 union the edge set of T2 union the edge E. We're just adding back in the edge E. All right. We're claiming that ultimately our picture is we have a tree T1, whatever it looks like, and there is a tree T2, and E is the bridge connecting them. Another way of saying this here Another way of saying this fact that you're going to prove is that every edge of a tree is a bridge. And that's actually the statement you're going to prove. What is a bridge? You remember from our discussion of all the terminology about connectivity last week? A bridge is an edge such that when you remove it via edge deletion, you increase the number of connected components. Okay, so in this instance, removing that edge increased the number of connected components by 1. Instead of having a single tree, you now have 2 trees. Okay, anyway, this edge set of T itself is the disjoint union of these 3 sets of edges. But we can count these now that we know that T1 has K1 minus 1 edges, T2 has K2 minus 1 edges, there's 1 edge here. So putting all those together, what is the count on the edges of T? It is k minus 1, or k sub 1 minus 1, that's from T1, plus k sub 2 minus 2, that's the number of edges in T2, or sorry, k sub 2 minus 1, plus 1, which is the single edge E that I'm adding back, right? And so this is, of course, k1 plus k2 minus 1, but k1 plus k2 is k. And so we have shown that if the inductive hypothesis is taken as true, then T also has k minus 1 edges. It's of order k, which finishes the induction. And that's that. Okay. One can similarly prove the following theorem. Think about how you would do this with induction, what you would induct on. So this is the following theorem for forests. So theorem. If F is a forest of order n containing k connected components, forest of order n, that just means it has n vertices. Okay, order always means the number of vertices. Containing k connected components, then F contains n minus k edges. Okay. The next two theorems, so again, the proof here is similar. Again, you can think about what you would do to complete that proof. The next two theorems can be thought of as giving alternative definitions of trees. We have a definition of trees that works fine, but these if and only if statements, when you say an if and only if statement, a way of thinking about that is that you are, you could replace if and only if with exactly when. So it is like a complete characterization, in a sense, of the behavior that you're talking about. So these next two things are saying, basically, if we, instead of defining it as connected and acyclic, what if we just chose, so connected acyclic implies that it's a tree. What if, knowing now that a tree has to have n minus 1 edges, what if we considered a tree to be a connected graph of order n that has n minus 1 edges? Is it necessarily acyclic? That's one question. The other is, if we have a graph of order n and it's acyclic and has n minus 1 edges, is it necessarily connected? And the answer is also yes. So that's what both of these are saying. So theorem. A graph of order n is a tree if and only if it is connected and contains n minus 1 edges. So quick proof. The forward direction, trivial by definition and our previous theorem. Not this one, the one on the other page. I'll put it back on, the one that we proved. This one. If a tree has order n, then it has n minus 1 edges. That theorem tells us that if we have a tree, obviously it has n minus 1 edges. By definition, it is connected and acyclic, so it's connected. So going this direction is easy. That's basically true by definition in that theorem. But let's go in the backward direction. This is the interesting one. So let G be a graph of order n and say that it is connected. It contains n minus 1 edges. So let G have order n, be connected, and have n minus 1 edges. We must show it is acyclic. That's the only thing missing. Therefore, a tree by definition. Okay. All right, well, how do we do that? We could say, well, suppose G has no cycles. Well, then it's acyclic and it's a tree. Okay, so we'd be done in that case. So then suppose that G does have a cycle, right? Suppose G has a cycle. Then we could remove an edge from the cycle, and the resulting graph would still be connected because it's a cycle. So removing an edge of the cycle keeps G connected. Right? In fact, we could do this one at a time from any cycles that exist, and we could maintain connectivity the entire time. We could do this one at a time for each cycle, maintaining connectivity. Okay. But then at the end of that process, the graph that we end up with would be a tree. We also don't have to worry about this process terminating or not. We know it terminates because these are finite simple graphs, so this is necessarily a finite process. I'm not going to have to remove infinite edges or anything. So there is an end of this process. At the end of this process, the resulting graph is acyclic and connected, therefore a tree. But if we've had to do this even once, right? If G even had a single cycle where we removed an edge and kept it connected and say we were done there, the problem is that we assumed that G has n minus 1 edges. But this tree would have order n, but strictly less than n minus 1 edges, which is impossible by our previous theorem. Thus, G can't have even a single cycle. If it had a single cycle, I could remove an edge, keep it connected. The vertices are the same. It has order n, but now would have n minus 2 edges instead of n minus 1 because I took away that one, which violates our tree theorem that a tree of order n has to have exactly n minus 1 edges. So this is impossible. So thus, G can't have a single cycle, which means it's acyclic, and therefore a tree, because it is connected and acyclic. This is showing you that you could have defined a tree to be connected and have n minus 1 edges of order n. Okay, so you could have defined a tree of order n specifically to be a connected graph with n minus 1 edges, not even referencing the fact that there are no cycles, and that would work fine for your definition of a tree, because it would still be the case that such an object would be acyclic. So that's what I mean by giving an equivalent definition of a tree. So this is just saying this is another characterization of how a tree behaves now that we know it must have exactly n minus 1 edges. Okay, let's see another example of this. A graph of order n is a tree if and only if it is acyclic and contains n minus 1 edges. So now I'm throwing out connectivity, right? So a graph G of order n is a tree if and only if it is acyclic and contains exactly n minus 1 edges. So again, forward direction is trivial by definition in our theorem. So the backward direction is what matters here. Now we don't have connectivity and n minus 1 edges. We have being acyclic and n minus 1 edges. So let G be order n and be acyclic with n minus 1 edges. We have to show that G is connected. Because if it's connected, then it'll be connected in acyclic and thus a tree. So that's what we're doing. We have to show that G is connected. So how do we show that this is connected? Well, let's say that it's not. Let's say it has some number of connected components. So let G1, G2, up to G sub k be the connected components of G. Now, here's the thing, right? We ultimately, if we want to show it's connected, we want to show that there's not k connected components. There's just one. So we want to show that basically G1 is the only one that exists. So that there's only one of these things. Now, since G is acyclic itself, then each of these is acyclic. Because a cycle in one of these connected components would be a cycle in G. So if G has no cycles, then none of the connected components can have cycles, right? So if G is acyclic, then each G sub I is acyclic. But by definition, the connected components of G themselves are, if we consider them as their own graph in their own right, they are connected. So each of the G sub i's is acyclic and connected, thus is a tree. So G is a forest. Thus has, well, let's go back to the theorem that we didn't prove, but I told you the proof was similar, and you can have a gander at it. Maybe that'll be another homework problem. If F is a forest of order n containing k connected components, then it has n minus k edges. So G is a forest. It is of order n. It has k connected components. So it has n minus k edges. But we've said that G has n minus 1 edges. And the only way that it can have n minus k edges and simultaneously n minus 1 edges is if k is equal to 1, i.e., there is only one connected component of G. Thus, G is connected. Hence, a tree. Okay. These sorts of proofs are good for building your intuition for how trees behave. Um, and so, what else do I want to say about like how these trees can look? Um, so the question is, okay, we have leaves in a tree, and then we have some other vertices that are not leaves. The question is, how many leaves does a tree have? Are there any leafless trees? Well, not really. Not really. In fact, the only leafless tree is the complete graph on one vertex, so just single vertex that has no edges. Any tree of larger order than that, so any tree of order 2 or greater, has at least 2 leaves, and that's the next theorem. Then T has at least 2 leaves. Okay, how does this work? The main reason I'm doing this proof is this shows another way how these induction proofs can be utilized, and this is something that is extremely common in a lot of these graph theory applications, to use induction in this way. So yeah, so how does this work? I'm going to be inducting on the order of the tree. Okay, so induct on order. So base case, start if n equals 2. If n equals 2, there's only one tree we have, and that's the complete graph on 2 vertices. So the result is true because it has 2 leaves. Both vertices are of degree 1 because they're only connected to each other. So result is true in this case. All right. Suppose this is the inductive step. Result is true for all orders. I'm going to write it like this. For all orders from 2 to n minus 1. And consider a tree of order n. Where n is greater than or equal to 3 to get us out of just the base case. Okay. So, by our theorem, we keep saying our theorem. This is our main theorem on trees, which is that they have n minus 1 edges. T has n minus 1 edges. Thus, since n is greater than or equal to 3, it has at least 2 edges. Okay. Now, if every edge of T is incident with a leaf, then T has at least 2 leaves, so you're done. Since there are at least 2 edges, if each edge is incident with a leaf, we have at least 2 leaves. That's it. We're done. So then assume that there is some edge of T that is not incident with a leaf. Call it E. Okay, and we'll even give it endpoints. We'll say that E is the edge connecting vertices U and V. So, as before, again, you're going to prove this on the homework that I assign later today. T minus this edge. Every edge in a tree is a bridge. T minus this edge is a pair of trees. Call them T1 and T2. Each of order less than n. So the inductive hypothesis applies to them, right? Less than n. Okay. Now, we'll say that we've labeled these in such a way that U belongs to T1 and V belongs to T2. So we can do this without loss of generality. W log, if you haven't seen that before, means without loss of generality. This just means I could have relabeled them however I wanted to. So I choose the labeling based on this. So let U be a vertex in T1 and V be a vertex in T2. Okay, and let the order of T1, the vertex count, be N1, and the vertex count of the tree T2 be N2. Each of those have to be less than N. Since E is not incident with any leaves, that's how we chose it, right? So we assume that there is some edge of T not incident with a leaf, so E is not incident with a leaf. Since this is the case, we know that N1 and N2 are at least 2. If they were not at least 2, then E would, the only way for that to happen is E being incident with a leaf, because if they were 1, then E would be incident with a leaf. That one vertex would be a leaf in the tree. So that's no good. So both of these are at least 2. And so the induction hypothesis applies to each of T1 and T2. And so by the inductive hypothesis applied to both T1 and T2, each of T1 and T2 have at least 2 leaves. Okay. Am I done now? Well, yes. I have to think here, right? So I'm going to draw the picture. Here's my graph. We'll call it T1. Here's the vertex U and T1. Here's the edge E that connects T1 and T2. It's the bridge between T1 and T2. Here's V. Okay. Since T1 and T2 each have at least 2 leaves, each of them have at least 1 leaf that is not incident with E. So each has at least 1 leaf not incident with E. Thus, the graph T minus E, where I've removed the bridge and then added it back in, that's just T, has at least 2 leaves. Because I can take the at least one leaf in both T1 and T2 not incident with E is my guaranteed 2 leaves. Maybe it has more, but right, this is a lower bound on the number of leaves here. Okay. One more theorem we're going to prove, then I'm going to state one more theorem, and you can read the proof if you want to, because all of these tactics that we've used so far in these proofs this will be good practice for you. So here's another theorem. In any tree, the center is either a single vertex or a pair of adjacent vertices. So the center of a tree is a very simple object, right? It's literally, this is saying that, well, no, I won't spoil it yet. After the proof's over, I'll say what it means. So how do I deal with this? If we're thinking of the center, right, then we're thinking of eccentricity of vertices. And so the idea here is using the fact that a tree has a very simple structure to basically think in our heads how to form a sequence of trees that we obtain through just deletion one at a time. Like one step at a time, we are going to be deleting leaves until we end up with something. So here's the idea. So given a tree T, form a sequence of trees in the following way. So let's initialize T as the tree we're starting with. So T naught is T, and let T1 be the graph obtained from T naught by deleting all of its leaves. So you're deleting all of the degree 1 vertices. Okay, you can think to yourself, right, this is vertex deletion, so you're also removing any edge that's incident with any of those deleted vertices. Okay, what does this do? First of all, natural question, is T1 a tree? It is. It is connected. And it is, how do I know it's connected, first of all? Well, consider what I'm deleting, right? Very quickly, let's test intuition, right? Test some intuition. So graph G, okay, has some number of vertices. If I delete a vertex V from G of degree 2, is the resulting graph G minus the vertex V connected? We'll say we started with a connected graph. Well, no, right? Here's an example. The answer is no. Here's an example. What about this thing? What about the path on 3 vertices? If I call this V, what is the path on 3 vertices minus V? It would be the empty graph on 2 vertices, which is not connected. Okay. What was the problem? The problem was I deleted a vertex that had degree 2, right? What if I delete a vertex that has degree 1? In fact, what happens to this graph if I delete every vertex that has degree 1? Well, there are 2 vertices of degree 1, these endpoints here. If I delete those, I'm left with K1, which is fine. What if I did it for a path like on 4 vertices here? If now I have 2 vertices that have degree 1, so here's a degree 1 vertex, here's a degree 1 vertex, right? If I delete each of these 2 vertices have degree 2. If I delete these 2 vertices, what am I left with? Oh, I'm left with complete graph on 2 vertices. Now, you could say, what happens if you delete both degree 1 vertices here? Well, then you've deleted all the vertices and you don't even have a graph, right? Remember, the empty graph has no edges. It doesn't have no vertices. We don't even talk about the object that is a graph with no vertices. That doesn't even have a name for us because that's not even a graph. So that is it. This is not even a graph to go further here. And this actually kind of encapsulates entirely what's going on with these trees. So of course P3 and P4 are both examples of trees. The question is, doing this process, do I ever end with something other than K1 or K2? And the answer is no. Okay, but it might take you a while to see that. So for instance, maybe in this, I could alter this picture again and say that we have P4, but I've put let's do something like this, right? All right, so whatever you want to call this graph, call it G. Where are the leaves of G? Well, they're here, 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 and here, right? Okay, so those are all the degree 1 vertices. If I delete those, I'm left with P4, right? So if I delete those, what I'm left with is the path on 4 vertices. From there, I can delete these 2 leaves, and I'm left with K2, right? And so you start to see how this sequence of graphs we form in this way is going to terminate, and it's always going to terminate in one of these. There's nothing else it can terminate as. If it terminates as something, if it terminates as P4, that's not terminating. You can go one more step, and here's what you end with. So for P3, you end with this. For P4, you end with this, and basically you're going to always end with one of these. Okay. All right. Now you might say, wait, does that depend on the order? Let's do one more example. Why not? Why not one more example? Here's a tree of order 5. What are the leaves? There they are. When I delete them, what graph do I end up with? K1 again. Okay. So, going back. So we delete all of its leaves. We keep this process going. Do I get a tree from this? Yes. So it turns out T1 is a tree. Well, remember, the thing we started with was a tree, so it had no cycles and it was connected. Deleting the vertices like this, deleting all of its leaves, leaves it connected. Okay, because they're degree 1, right? That was the other thing I was illustrating with those examples, is that when you're removing degree 1 vertices with vertex deletion, you don't have to worry about connectivity. And so stays connected. It stays acyclic because you're removing vertices. So if it already didn't have a cycle, it's not going to gain a cycle through vertex deletion. And so this is guaranteed to be a tree. Continuing this process from T1. All right, so continue this process. To obtain a sequence of trees. So T0, T1, T2, and so on, all the way to some T sub R. So how do you, when I say continue this process, what does it mean? It means from the prior tree, you remove all of its degree 1 vertices, all of its leaves. So to get to the next step in this sequence, so T2 is obtained by deleting all the leaves from T1, T3 is obtained by deleting all the leaves from T2, and so on, all the way you get to T sub R. Since this is a finite simple graph, since T is finite, there exists some natural number R such that T sub R is either K1 or K2. So as I indicated, those are what you end up with. Okay, you can try this process yourself. Pick your favorite tree of order 10 and do this in sequence. Delete all the leaves at each step. At the end of that process, that process terminates exactly when you end here. There's no other way it can end. But now you actually kind of see what it is that's going on, right? We said that the center is either a single vertex or a pair of adjacent vertices. Well, what are K1 and K2? K1 itself is a single vertex. K2 is a pair of adjacent vertices. We're saying that this thing we get at the end of this sequence is the center necessarily. Okay, that's what we're saying. So now we just have to prove that it is in fact the center. So consider a consecutive pair of these trees, say T sub I and T sub I plus 1. Okay, let V be a non-leaf of T sub I. Since it is a non-leaf of T sub I, it will be in T sub I plus 1 as well. Okay, of course, in T sub I, the vertices that are at the greatest distance from V are the leaves of T sub I. Necessarily. So that the eccentricity of V in T sub I plus 1, which it's guaranteed to be in because it's a non-leaf of T sub I, is 1 less than the eccentricity of V in T sub I. Thus, eccentricity of V in T sub I plus 1 is 1 less than the eccentricity of V in T sub I. But this is true for all non-leaves of T sub I? Like, there's nothing special about V? But then, what has to be true in that case? This is true for all non-leaves of T sub I. So then what is the center of T sub I compared to the center of T sub I plus 1? This implies that the center of T sub I plus 1 is the same as the center of T sub I. And this is the thing that finishes it. We're done once we realize this. This process, as like harsh as it might seem in terms of vertex deletion, you're like massively reducing the order of the graph potentially at every point, right? In that one example that I drew, we went from an order 5 tree to an order 1 tree in a single step. So this seems like it may be a brutal type of surgery you're doing on the graph, but whatever it is, it doesn't alter the center. In fact, if we go back to, say, this example, if I asked any of you what is the center of this graph, everyone would immediately identify that's the center. Well, in this step, all these leaves get removed, and I'm left with this, which is the same, this corresponds to the same vertex here. So even going in this one brutal step, does the center change? No, the center of this graph is that vertex. The center of this graph is that vertex. Here, the center is this vertex, right? And when I delete the leaves, I'm left with that vertex. Here, what is the center of P4? It's these vertices. These two are the center. Removing the leaves, I'm left with those two. Here, what is the center of G? The center is actually these two. When I delete the leaves, I'm left with this. Again, the center is these two. Going one step further, deleting the leaves. Again, the center is the same. Okay, so we're saying that this is true in general, that the center is not altered here. But this means that the center of your end thing is the same as going all the way back the center of T naught, which is T. But T sub R is either K1 or K2. So the center of T is either one vertex or a pair of adjacent vertices. And that's it. Okay. Again, I wanted you to see the full sort of argument that happens in these sorts of proofs involving trees because they're useful for answering a lot of these questions you're going to be asked about trees. Okay, one more theorem. I'm not going to prove this one. I'm just going to tell you where the proof is. So, following theorem, let T be a tree with K edges. Of course, if we know the order of T, then we know exactly how many edges it has. But let's say T is a tree with K edges. If G is a graph whose minimum degree which we use delta, lowercase delta, to uh, define, satisfies that it is greater than or equal to k, then G contains T as a subgraph. Alternatively, G contains every tree of order at most minimum degree of G plus 1 as a subgraph. And the proof here is on page 37. Okay. Pick a graph and pick a graph and have its minimum degree be like, I don't know, we'll say 3, right? Have its minimum degree be 3. Okay, then find your favorite tree of order 4. There's not too many of them. And see it as a subgraph of that graph. Okay, you can up that minimum degree requirement to see what you can find here, but this is saying that this is giving us a condition on a graph containing a tree as a subgraph. Okay. Now, remember at the beginning of lecture today, I gave an example of a tree, or rather even just a graph, that had weights assigned to the edges. Okay, and so we can discuss the notion of a weighted graph in the following way. So definition. Given a graph G, a weight function W is a function that maps the edges of G to non-negative real numbers. Now, this requirement that it be non-negative, we don't have to have that. There are contexts where having negative weights to edges would make perfect sense, but for now we're going to focus on the instance where the weights correspond to a non-negative number. Just to simplify things a little bit, but again, this is not super important. There are absolutely applications where having negative weights would make sense. These taken together, so a graph G together with a weight function. So the thing I was defining here is a weight function, but also I'm defining weighted graph here, is a weighted graph. So an example of that, of course, might be something like this. So 10, 5, 1, 37. Put pi here, put e here. Let's put a square root of 2 here. 55, 17. Okay. So here's our weighted graph. The weight function is obvious here. Like you're almost never going to see W actually written in function notation or anything. The weight function is obvious here in the sense that, oh, it assigns this edge the value of 10, it assigns this edge the value of 5, and so on. Okay. So this is how a weighted graph looks. There are many reasons why you would talk about weighted graphs. So some of these applications are going to be very obvious and mundane. Some might be a little bit more esoteric. There are applications in some pretty high-powered differential geometry stuff of essentially weighted graphs that take the name train tracks. And there's some pretty high-powered stuff that goes on, and this is, as I said, this is very abstract differential geometry stuff going on. And this wasn't fully brought to bear until like the 1980s, which might seem like a long time to you, but mathematically speaking, math done in the 1980s is like absolutely brand new. Like if you're studying pure math, you're not going to be looking at math done in the 1980s until you're basically finishing your PhD. So, up until then, like by the time you get out of undergrad, you're going to be doing math that's 120, 140 years old. Uh, so yeah, math done in the 1980s is like absolutely brand new if we're talking about pure math. So anyway, but there are also some very mundane applications of these things. So I'm going to give you one example that is like we could call it like a city graph. Or like a road network graph. So I'm going to I'm going to draw a picture here and then I'm going to read some stuff. So let me draw a nice picture so I don't have to keep holding up a book. That would be very nice. So the idea here, and I believe at least one of the authors of this textbook is from or teaches at, I think one of them teaches at App State, so they live in Western North Carolina, or I guess did when they wrote this. And so they have an application coming from the North Carolina Department of Transportation, which is the following. I'll give the rundown here in a second. I'm going to label these vertices first. Again, like I said, so that I don't have to keep holding the book up. I think it's actually better to do it this way. So what this graph is giving is essentially the following. So North Carolina Department of Transportation has decided to implement a rapid rail system to serve 8 cities in the western part of the state. Some of the cities are currently joined by roads or highways, and the state plans to lay track right along these roads. Due to the mountainous terrain, if you've ever been to western North Carolina, I'm from East Tennessee, so there's a part of Interstate 40 that connects East Tennessee to western North Carolina. It is called the Gorge. It is a stretch of, I believe, 45 to 50 miles where there is not a single exit. It is through absolute mountain wilderness. There is nothing there. If you run out of gas in that stretch, you're screwed. Now most of it, or some part of it is closed now due to mudslides and things from last year and all the flooding. But But that whole stretch of the interstate is absolutely miserable to traverse in any kind of if it's raining or something. It's just annoying because you are all the time you're right next to a bunch of like semi trucks on these very windy mountain roads where there's almost no shoulder. It's pretty horrifying. It's pretty annoying, honestly, to traverse. But anyway, so it's very very mountainous. It's not you're not able to just draw a straight line between two cities and be happy with it. On account of this, laying down track, even when a road exists, is not going to be equally easy in all directions. And so a consultant was hired to actually make a city graph that essentially ranked the difficulty of connecting cities. So I'm going to label some of these cities. This one's Marion. This is Hickory. Here's Lenore. Here's Blowing Rock. Here's Linville. Banner Elk. Boone. And Jefferson. I think that's all of them. And anyway, a consultant was hired to essentially rate the difficulty of laying down track between two of these, any two of these cities. Of course, I'm just going to go ahead and label these. So I think the rating was done from like a 0 to 100 or something. So the highest rating corresponds to the more difficult track to lay. Rating accounted for length, grade, curviness of the road. Higher rating corresponded to greater cost. Yeah, so it would cost more depending. And so here were the weights assigned. So here was 10, here's 20, here's 20. And I mean, depending on the context and how good the consultant was, maybe these numbers even correspond to like estimated costs, right? So maybe you can imagine an application where these numbers actually correspond exactly to the cost, so that coming up with a way to traverse all of these in an efficient manner or cost efficient manner or cost optimizing manner is like just directly a thing that you're doing when you're trying to find the object that we're talking about. And so here's the thing, in this context, right, since you might say, why don't we just lay down railroad track that connects every city to every other city? Of course, ignoring geography and ignoring budget and ignoring all that, of course you could do that. That is a solution. But it's not realistic and it's not maybe the most efficient solution. So the idea wouldn't necessarily to be to connect every city to every other city. That'd be ridiculous. But also, even laying down tracks as indicated here wouldn't be that useful, because for efficiency's sake, what does a cycle correspond to? Right? Like a cycle would be, say for instance, this cycle in the graph. If I were to lay down train tracks according to these roads here, so if I'm just I was using the roads here to dictate where I was laying down the train tracks parallel to them. If I was laying down train tracks here, what would this cycle represent? This cycle would represent a like train track circuit or cycle between cities Linville, Marion, and Lenore. But the reason why that's not super efficient is, rather than having all of these accessible in this way, it would be more cost effective to not throw down all of this track. If you wanted to go by track to from Marion to Linville, rather than having this option, maybe you go to Lenore and then to Linville instead, so that you remove this part of the cycle and make it not a cycle. The point, I guess, that I'm trying to say here is that for this application, a cycle is inefficient in some way, right? A cycle would correspond to a segment of wasted track, right? So note, a cycle would correspond to a segment of wasted track. So then what do I seek? I seek a, we'll say a subgraph here that wastes no track. So this means no cycles. Connects all cities. Is connected. So already, no cycles and connected. What is the thing that connects all cities? So it has all of these cities, all these vertices are included in the subgraph. It wastes no track, it has no cycles. This is referred to, these two things are referred to as a spanning tree. So a spanning tree, notice that it is definitely a tree because it is acyclic and connected, but because it connects all of the vertices, it spans the whole graph G. So if this is G, this is what I call G, then the T that I seek is a subgraph of G where I have no cycles, but everything is still connected. So I've thrown out some of these edges in a way that turns what's left into a tree on all of these vertices. That is known as a spanning tree. Now, since we have these weights, if these weights are corresponding to the cost, I want to minimize the cost. So I seek, ideally, a subgraph that wastes no track, connects all cities, and minimizes costs. Or minimizes whatever the weights, right? Minimizes weights. Right? Of course, you might say, what if I want to maximize the weights? Well, you could just recalibrate your your weights in such a way that that minimum is the good one, right? Like you just flip them around. Um, but the same argument works, right? Remember, max is just minus min. Min is just minus max. It's fine. So okay. So then this is a spanning tree that minimizes the weights. If it does all of these things, so T that does all these things is known as a minimum weight spanning tree. And so that is exactly what we seek here. We seek a minimum weight spanning tree. Okay. You might ask yourself whether so what does this mean exactly? Minimum weight here means that, might you have a spanning tree that also satisfies all these and has the exact same weight sum as another? Yes, it just can't be less than that. Okay, we're actually going to see here that this does not have a unique minimum weight spanning tree. So a big question, is such a thing? If it exists, and it is going to exist, as we'll see, is such a thing unique? And the answer is no, as we'll see. In this example even, you're going to see how it's not unique. Okay. Now, what I want you to think of for a second is, and you can even pause the video and do this if you're watching it later, think of looking at this, how you would cook up a minimum weight spanning tree just kind of intuitively. Because if you really put some thought into this, I promise you that what you come up with is going to be roughly the same as the first algorithm that we discussed that does this. Okay. So think about it for a second. It's not going to be some black magic. It's not going to be something. So, occasionally, right, in math, you come across a solution to a problem, the basal problem that Euler solved. That's the type of thing that is like it's like a true stroke of genius where you're like, man, I could have thought about that for weeks and not come up with that solution. That's not going to be how this works. You're going to see how this works well enough that you're not even going to have to like train yourself to remember this algorithm. You're going to immediately remember it because it's that intuitive and it's that obvious in the sense that it's just kind of the thing you would obviously do to get this done. So, to that end, we discuss Kruskal's algorithm. So, given a connected weighted graph G, one, find an edge of minimum weight and mark it. Two, among all of the unmarked edges that do not form a cycle with any of the marked edges, choose an edge of minimum weight and mark it. So, among all unmarked edges that do not form a cycle with any of the marked edges. So basically, you're making sure that the next edge you mark does not complete a cycle. That's what you're doing here. Among all the unmarked edges that do not form a cycle with any of the marked edges, find an edge of minimum weight and mark it. Three, if the set of marked edges forms a spanning tree of G, stop. If not, repeat step two. Why did I put two P's here? If not, repeat step two. This does it. I'm going to show an application of this here in just a second. But the fact is that you will see when you see the algorithm in action, you will see how this works. I'm not going to do the proof that this gives you minimum weight spanning tree, although the proof is not that long. It's on pages 41 to 42. Kruskal's algorithm produces a spanning tree of minimum total weight. Okay. Let's see how this goes. Okay. Now, just to refresh your memory here. Find an edge of minimum weight and mark it. I think I answered this question before that I don't. I just have a bunch of black pens here. I was looking for if I had different colored pens, but it seems like I do not. Oh, that's fine. So, minimum weight, minimum weight. This is, of course, because this graph is small, I can do it with my human eyesight just fine, but you can imagine having all of these weights in computer, this is very amenable to computer computation of finding minimum among the edge weights. Here it is, right? 10 is the smallest edge weight, so I mark it. There it is. Okay, so it is marked. Next step. Among all marked edges, among all unmarked edges that do not form a cycle with any of the marked edges, choose an edge of minimum weight and mark it. So, let's see. You might think that hidden in there is a bias toward being connected to the path you've marked, but that is absolutely not the case, as we'll see in one of the steps here. But here, I have an option, right? I could choose this one or this one. They're both 20. I'm going to pick this one just because, but we're going to see how this leads to non-uniqueness, for instance, in this example, because I could have just as well have chosen this. Okay. And so here's what I get. Okay. Next, I still don't have a spanning tree because I'm missing a bunch of vertices here, right? I'm only hitting 3 vertices. So I'm missing 5 vertices still. So I definitely still don't have a spanning tree, so I have to keep going. Among all the unmarked edges that don't form a cycle with any of the marked edges, I'm looking for the smallest one. There it is. So I mark that edge. Again, I still don't have a spanning tree. One, it's disconnected, right? It's not even connected, so this has no hope of working. Next, I'm looking for the next edge that of minimum weight that doesn't form a cycle with any marked edge. So, and again, notice that that excludes this, because technically this is the next minimum weight. I mean, it already was before I even marked that, but marking this edge would form a cycle, so I don't do that. Here I have weight 30, which is the smallest from the remaining weights that are unmarked. So there we go. There it is. Again, still don't have a spanning tree. So I say, okay, well, from the remaining unmarked edges that don't form a cycle, this one is of minimum weight. Okay. Next minimum weight is this one. Still don't form a spanning tree because I missed this vertex, and so the last edge to be marked is this one. And what I have ended up with is a minimum weight spanning tree T. You will notice that it hits all vertices, so it's definitely spanning tree. It's a tree, has no cycles, right? But it's connected. And it is minimum weight. Either you can just check that it is minimizing. Of course, notice I could have chosen this. So is such a thing unique? The answer is no, because I could have chosen this and not chosen this edge. I would have still ended up with a minimum weight spanning tree. So this does not yield a unique minimum weight spanning tree. They're not unique in that sense. But they are, unique up to the weight, right? The sum total weight. So, for instance, choosing this other thing wouldn't have reduced my weight any further. Wouldn't have increased it either, but it wouldn't have reduced it any further. And so that is one algorithm for finding minimum weight spanning tree. It is definitely not the only one. There are others. You're going to see an example of another in homework. So homework 2, you're going to see Prim's algorithm, which is similar. You can convince yourself that it equivalently always gives minimum weight spanning tree. Um, and yeah, anyway, it is easy to see how useful this would be in answering these problems or these application problems coming from such a thing. And that in this instance, it was like a city graph, right, where the connectivity was something about a length or a cost minimizing effort while still getting everything from the train tracks that you want. Anyway, that's that. We're going to continue on with trees tomorrow, but I think that's pretty much it for today. As I said, I will post your second homework later this evening. It will be due this Friday. I'll let you know about that. I'll post that problem set to Elms, and I'll post an announcement when I do. So anyway, that's all for today. So I will see you all tomorrow.